Okay, back with another stream. Okay, so now that we have the Schwartz-Zippel lemma, okay, well, obviously it's not compiling or whatever, but we're going to move on from that slightly and try and figure out how we can make use of this lemma now that we have it. Okay, so the main way that I want to use this is I want to make a modification of the ring tactic defined here that uses the Schwartz-Zippel lemma instead of just putting both sides of the expression in a normal form and like comparing them. Okay, so this is the base level ring tactic. There's also ring NF, which is for sort of normalizing. That's not what I want to do, so probably I don't need this. And then I've copied this into like ring/Schwartz-Zippel.lean. And so the basic way that it works, this is the basic way the ring tactic works, is it has, okay, it's a mutual induction, right? This is something I noticed of, so we've got like the base expression, so we have like these polynomial expressions. We have the base of the exponent expression, we have product expressions, and we have sum expressions. And so, yeah, I don't know why it's called x base. Shouldn't it be called x exp? But whatever. I mean, the idea is that the base is either an atom or it's a sum. What? That doesn't make sense. Why can't it be like a product, for example? Okay, maybe there's just something I'm not understanding. So it can be, okay, so the point is that if I have a sum, then, right, in theory, like the base of the exponent could be a product, a sum, or an exponent, or an exponential expression. And so the point is that if it's a sum of monomials, what? Why is sum called out here but not mul? I don't get that. An atomic expression E with ID. Atomic expressions are those which ring cannot parse any further. Okay, for instance, A plus A mod B has A and A mod B as atoms, right? Because A mod B is not a ring expression. Ring 1 tactic does not normalize the sub-expressions in atoms, but ring NF does. The sub-expressions in atoms. Atoms, in fact, represent equivalence classes of expressions. Okay, this is annoying. Why does it... It, like, gives me a tooltip. A tooltip about inductive types. It's just telling me how to define inductive types. Okay, I don't need that information. Atoms, in fact, represent equivalence classes of expressions. Right, modulo definitional equality. Why is that? The field index of type n should be a unique number for each class. The base of a normalized exponent expression. Okay, maybe I'm like misinterpreting this. This is not like is this defining the type of like ring expressions? Not totally obvious to me. Or are these like specific? Okay, atoms in fact represent equivalence classes of expressions modulo definitional equality. The field index of type n should be a unique number for this class. The field index should be a unique number for this class, while value contains a representative of this class. The function resolve atom determines the approximate atom for each for a given expression. Does this show up? Index. I'm like slightly nervous that this is from like the old ring, and so it's not in any way like a actual explanation of the code that I'm reading. A monomial, which is a product of powers of x base expressions. a product of powers of x base expressions. Okay, so what I'm trying to determine if, like, does this set of a sum of monomials, right? It can be a sum of monomials. Okay, I mean, like, we go crazy here with the base and the product and all of these. Okay, a monomial which is the product of powers of x base expressions. Okay, so I guess maybe the idea is that I can have a sum in a base, but I can't have a product in a base, because if I have a product in a base, I'm supposed to distribute over the exponent. Interesting. Coefficient value, which must not be 0. E is a raw rat cast. If value is not an integer, then type should be a proof of value dot den a is not equal to 0. Okay. Okay, it's a monomial, so it has a coefficient value, a product x to the e times b. Oh my god, this tooltip is so annoying. Okay, I'm just not going to touch the mouse. A product x to the e times b is a monomial if b is a monomial. Here, x is an x base, and e is an x prod, representing a monomial expression in n. X is an x base, e is an x prod. Product of powers of x base expressions. E is an x prod. What? So I mean, I thought the rule for ring was that you can't have like non-natural numbers as exponents, right? Huh. Monomial expression in n. Okay. X prod, E is an X prod representing a monomial expression in n. Okay, well maybe the idea is that, like, okay, the idea is that it can in fact handle a plus this. It can handle this. Okay. So it's not that it just has to be like 2 or some like literal, some literal natural. Mul. Okay. And this is using like the quotation library. This is what all these Q's are. Okay, so SA is the com semi-ring instance. S alpha is the com semi-ring instance. X, E, and B. Right, so we have a base, we have an exponent, and we have like a coefficient. B is a monomial. If B is a monomial. Okay, I guess the point is that B could be anything, really? Not clear. Okay, it takes an X base and X prod of naturals, right? So this is the base, the exponent. I think this is the exponent. And then B, and then it returns this. Okay, some weird expression. Polynomial, okay, the sum, EX sum, which is a sum of monomials. It's mutually inductive. That's the point. So I could get a sum by taking a sum of monomials. So, okay, so X sum, let's like look at the last line here. It can either be 0, which is fine, or it can be add, in which case it is an addition, right, of a sum and an X prod. So basically the point is, like, if I'm doing a sum, I'm going to break my sums down into like left-leaning trees or right-leaning trees, and the left side is going to be like a product. Left-leaning, right-leaning. I guess it's right. The point is that, like, if I have a whole bunch of products, I do like one product and then the sum of the rest of the products recursively. Mutual. Partial only. I don't know what the syntax is. Does this mean that this is the end of the mutual definition block? The mutual inductive definition block? Okay, so a sum is basically a bunch of products. A product is... Okay, I think I understand. So by the same principle, a sum is just if I have a bunch of individual product terms, I can sum them all up in like a list. And by the same token, the like x prod b serves the same purpose as x sum b here. The point is just that like I'm splitting off an exponential expression, right? So like x and e here represent the exponential expression. And how do I achieve the exponential expression? Well, it's just well, I have to use x sum again, right? Because I can have a sum of things inside the base. I can definitely have a sum of things inside a base. That's allowed, right? I can do x plus y equals x squared plus 2xy plus y squared. X plus y squared. A sum of monomials. So x base. The base of a normalized expression. Okay, so I think I'm beginning to understand, right? The base is an expression of type base. And then there's the exponent here, which is of n, right? It's like of type n. So the exponent always has to be a natural. So this is the base. Like it's all of this is like a sort of inductively defined list where we have the x base and the x product, and the x bases are always like sums, right? But they can never be products themselves, because I think that if they were products, we would want to do the induction in here. Okay, well, that's not confusing. So we have this. This is totally antithetical though to everything I want to do, because the whole point of using Schwartz-Zippel is that I do not necessarily want to have to normalize my expressions. Okay, is it possible to like construct one of these? It says it's a normalized exponent. The question is this whole inductive like type set of mutually inductive types here, do they mean that I can only express terms in a way which is already normalized? Right? For example, can I express, if I want to express a plus b quantity times c plus d quantity, right, times quantity c plus d, right? Can I express that notion? Right? The point would be the base e of a normalized exponent expression. Yeah, how do I express that? That's what I want to know, right? If I have a plus b times c plus d, how do I express that? So it would have to be as a product, right? And so it would be a product, and then it would be, right, so it would be a product of two things, and I guess both of those would be like x bases. But is the point that I'm supposed to like artificially insert insert 1 as the exponent? That doesn't make a lot of sense to me. Maybe the reason, maybe it is just assume that I insert 1 as an exponent. If I don't want to do that, there should be a hint to that somewhere else in the file, probably. If it is the case, right, it strikes me that I can just insert 1 as the exponent. And if that is the case, then it's good, because it means that these expressions are not necessarily normalized. And that means I can potentially use them. Let's continue to read. EX base equality. Equality test for expressions. Right. Okay, I think the point is this mutual block is for the rest of this, because like now that we've defined this like three-way mutually inductive type, all of our like future inductive definitions are going to have to be like over all the possibilities. So the point is that the two base expressions are equal if either they're both atoms or they're both sums, and if they're sums of the same thing. Heterogeneous equality. Oh no, this is Boolean equality. Wait, they've redone it. Boolean equality is now equals equals. It used to be that equals equals was heterogeneous equality. Okay, it's good that it's not heterogeneous equality because I don't want to deal with that. Okay, so yeah, x base is this, x prod. Right. Equality test. Inherit doc. Right, because it's a three-way. Okay, this is interesting. It's like it's not smart enough to realize that because these are mutually like defined, that they should all have the same doc string. That's sort of funny. But anyway, this is just saying that like all of the like component parts have to be equal. Like for example, if it's mul, then right, A1 equals B1, A2 equals B2, A3 equals B3. Yeah, it's just everything, like, they have to be exactly equal as trees of expressions. Okay. Yeah, expressions, they have to be exactly equal as trees. Cool. And they all return bool is the thing. That's interesting. But I guess it makes sense that it returns bool rather than EQ. I wonder if it's like lowercase eq for bool and capital EQ for like prop equality. I don't know. Okay, yeah. So exactly equal as trees. What does this part tell us? Compare. This is a total order on normalized expressions, and it's just gonna be like a lexicographical order. Yeah. Atom sum. Yeah, if they're two atoms, then I compare them. If they're two sums, then I compare the like individual components. Like if they're different, then I can make a decision. If they're different, I can make a decision. Yes. Yeah, then. Yeah, makes sense. Cool. Compare. Sorry, what is ordering? I just like, this is a type with 3 elements, right? Yeah, right. All right, cool. Yeah, so we have a total ordering. That's fun. Instance inhabited. Yes, they're all inhabited. That's A-okay. Cool. Mutual cast converts x base SA to x base SXB. Okay, what is this? So this is these are like the COM semi-ring instances, right? S alpha and S beta are the COM semi-ring instances. Okay, this is like sum type. This is not sigma as in sum, it's sigma as in like the dependent type theory thing. Converts, assuming 2. Okay, I don't know why we would ever have different COM semi-ring instances, but I guess that's okay. The result of evaluating an unnormalized expression E into the type family E. Structure result. Okay, what is this? Okay, so we like there's no more mutual definition. That's interesting. Well, they have an end, right? The end is the end of the mutual, so the end goes with the mutual. Yeah, cool. So that seems fine. Okay, what is result? Structure result. Result. The result of evaluating an unnormalized expression E into the type family capital E, 1 of x sum x prod x base, is a normalized element E prime. Yeah, the really weird thing that I don't understand is why did you have to make 3 different types mutually inductive when you could have just made, this is like, why does it have to be a mutual induction? Why can't it just be a single induction? Why can't it just be a single induction where you can have like addition of two things of the type, or products of two things of the type, or exponents of two things of the type? Oh, right? It can just be an inductive definition with like, you know, cram all of these in. Why does it always have to be left-leaning trees? Okay, yeah, another mystery for me. Result. Reading it again. The result of evaluating an unnormalized expression E into the type family E is a normalized element E prime and a representation E prime for it and proof of E equals E prime. Cool. A representation E of E prime for it. Evaluating into the type family. The type family E. Okay, I think what this is trying to say is the type family E is the like is the set of these three types, right? This is the is a normalized element E prime. Normalization. Okay, so maybe the point is that it's a little bit normalized. Unnormalized expression E into the normalized element. Okay, so maybe they're calling it normalization, but it's not necessarily normalization. This is where like the question of, am I supposed to like put a 1 exponent on expressions that don't have an exponent in them? Structure result. A of type Q, E of type Q, A of type. The data associated to the normalization. A proof that the original expression is equal to the normalized result. Right. I mean, so this is, I mean, it strikes me this is similar to the thing that like the tactics always do of like, okay, like you have this, and you have the thing that proves that they're equal, and like it allows you to like compose that later. Instance inhabited, inhabited result E. Okay, like E. It's weird because like they say the type family E. I think the type family E is supposed to be like this sort of union of these three, but it's also like a variable here. So maybe the point is that it's passed as a variable. The type of linear expressions having type A, and it returns a type. So maybe the point is it returns one of the three types of interest. Okay, so something else is inhabited. Yeah, I'm fine with that. Variable. Okay, so now we have some variables. We have alpha, S alpha, and con semi-ring. Wait, where is R defined? Is it like a auto implicit or something? I don't see like a definition of R. I assume it's like an auto implicit. Okay. Yeah, it strikes me that this version of this library is from before there was auto implicit. So I might have to might be like prudent to like pull master or something. Yeah, let me just let me try that. What happens if I... Okay, so this is the Schwartz-Zippel. This is like the copy of this, but if I go back here, okay. Variables. Sorry, where was that variable that I found? Am I insane? I literally just copied this. Line 229. 229. Con semi-ring R. what happens? Okay, but what happens if I pull? Pull from... Wait. Was that right? Does this have origin? Okay. Oh no! It's very unhappy. Okay, did it tell me what went wrong? Okay, yeah, it always like git config. You have divergent branches for your next pull. Okay, well, I want to run that one, so give me a terminal. And then, now that I run that, let me try the exact same command again. Git pull from math.i4 origin master. The inversion changed, okay. Okay, so it didn't change. I'm not exactly sure what happened here. Yeah, just maybe it's the case that like single letter variables, they were talking about how single letter variables, they were maybe going to let those be auto implicit. Okay, whatever. Let's keep reading. xprod.makeNat constructs the expression corresponding to .const n. The .const constructor does not check that the expression is correct. MakeNat n e. Okay, so it turns it into a quoted type e. Is the type of Lean expressions having type alpha? So it's an expression, right? It's an expression. So it's an right? So e, right, is an expression, but it's an expression representing something, and that thing has a type, and that type is alpha. All right, cool. So it gives us an expression, and also a monomial. Yeah, that's fine. Cool. Make negative nat is much the same. Okay, except here, of course, it's like a ring, because it can't be a semi-ring if you're going to have negative numbers. That's fine. And then make rat if it's a division ring. That's cool too. Constructs the expression corresponding to .const negative n. Cool. Yeah, I like expect that what's going to happen is if this ever makes it into MathLab, which it won't because it's not a good idea to add it to MathLab, but if it ever did, it would be like a sort of weird nightmare of my thing only working for division rings and giving horrible errors for other things. Because I'm basically going to assume throughout all of this that I'm working on a division ring. Okay, so we have a new section here. Now we have some more definitions. Embed an exponent multiplying by 1. Oh, wait, yeah, we do have the multiply by 1 thing here. Embed an exponent, x base x prod pair, as an x prod by multiplying by 1. No, it's multiplying by 1. What? Okay. Embed x prod in x sum by adding 0. Okay. Right, we have to, okay, this is the point. The point is that like we need to deal with the like very end of the left leaning tree here. Because we need to deal with the very end, we need to like make these embeddings so that we can actually like make these expressions. xprod.coef. Get the leading coefficient of an xprod. Okay, cool. Two monomials are said to overlap if they differ by a constant factor, in which case the constants just add. Yeah. When this happens, the constant may be either 0 if the monomials cancel, or non-zero if they add up to something other than 0. The 0 case is handled specially because when we hit the 0 case, we need to cancel out the thing. So the expression E, the sum of the monomials, is equal to 0. Again, it's like a type rather than a Q is nat E nat lit 0. The expression E, the sum of monomials, is equal to another monomial with non-zero leading coefficient. Non-zero result x prod SAE. Okay, it's a result. Right, I guess the point is that like we need to also be keeping track of like the fact that we know that it's equal to 0 because that will be crucial to construct the proof later on. So it makes sense that it would be like a result here. Oh shit. I need to move my magnets so I don't kick them. Overlap. Add overlap PF. X in ring. Okay, so this is just a, okay, so here we have a theorem that has nothing to do with like tactics, which is, thank God. It's just to say that A plus B equals C implies A to the E times A plus X to the E times B equals X to the E times C. Would be good to have this. Yeah, so like I can see how these are structured. It's X to the E times C. Right, it's just distributive of multiplication over addition. Yeah, cool. We'll add. And of course you can't prove it by ring because this is the ring file. That's fun. Add overlap PF0 is nat A plus B nat lit 0. Assert that an element of a semi-ring is equal to the coercion of some natural number. Okay, nat lit 0 constructs raw numeric literals. Okay, so this is like if we can prove that A plus B equals 0, then is nat this is in fact equal to 0. Right, by simp molad, sure. Simplifier handles it. Given monomials VA, VB. Okay, this is eval add overlap. Given monomials VA, VB, it attempts to add to them. Okay, so this is where we get to like the meat of the. Okay, I mean technically we're only like a third of the way through this file, but we're starting to get into some actual stuff here. Here, let me like close this little alert. Eval add overlap, option overlap. Result overall rat. Yeah, the fact that I don't have the right lean version is gonna rear its head at some point, but I'll just deal with that later. Monomials VA, VB. Attempt to add them to get another monomial. If the monomials are not compatible, returns none. Okay, so that's like an error condition. For example, xy plus 2xy equals 3xy is a dot non-zero overlap. A dot non-zero overlap. Whereas xy plus xz returns none, and xy plus minus xy equals 0 is a 0 overlap because they cancel out. All right, cool. Eval add overlap. Okay, so this is the 0. This is where it's none. Constants EAHA, constant BHB. Do let RA equals this, RB equals this. Right, if it's two constants, right? The point of it, if it's a constant and something that is not a constant, then it's none. Then we deal with the case where they're both constants and the case where they're both moles. And then we like have to determine if VAB, VB3, VA3, VB3, if they have this add overlap thing, if we get 0 out of that, then we have to like return the fact that it's 0, and if it's non-zero, we get a non-zero. And that's sort of the same thing goes on up here. Okay, that's fine. Okay, here is just some random facts about semirings, some theorems that we need. Yep. Add, proof, add, overlap. Okay, val add. I mean, what I'm searching for here really is where in this whole thing are they doing the actual normalization? What I would really like to do, right, I mean, how I would like to structure my tactic is that I would like to take my like equality of expressions, and I would like to turn them into multivariable polynomials, really. Yeah. Once I have them in the form of multivariable polynomials, then I can start to decide if they're equal or not. Like, I want to prove that the expression is 0 by, like, this expression is the evaluation of this multivariable polynomial on these values. Furthermore, it is the 0 polynomial. Therefore, the evaluation is 0. That is how the structure of that proof should go. All right. So if I'll add a plus, okay, so I mean, it's just sort of telling us what's going on in the comments here. Adds two polynomials to get another normalized result polynomial. 0 plus b equals 0, a plus 0 equals 0. A times x plus a times y equals a times x plus y. Uses eval add overlap, right? It determines, just a sec. It recursively calls itself, right? Yeah. Right, if A1 is less than B1. So the point is that at the same time, like, it's also sorting the things. Right, it's doing like a sort. Because if A1 is less than B1, then it needs to, wait a minute, just a sec. If B1 is greater than A1, right, okay, so the point is that I have two expressions, which are sums, right, and the sums are, of course, themselves lists, right, and so to sort them, it's basically merge sort, right? Think of, like, replace the, like, plus here with a plus plus, and replace the plus here with, like, colons here, and it's just merge sort. It's like B1 with A1 plus A2 merge B2. Yeah. It's interesting. Because the expressions themselves are always sorted, So I don't have to like worry, like by construction. I think the point is that like these addition expressions, right? Like an add, right? An add all the way up here. X sum, right? Like, right? It's like this list of sum expressions. I think the point is that by construction, it's always sorted, or at least like whenever one of these elements is constructed in this file, it's always as a sorted element. Right? Because we don't have to prove that things are non-equal. I think the tactic just fails if things are not equal. So we don't have to worry about like weird malformed things. We don't have to like worry about tracking and non-equalities is the point. So where was I? I was here. And so because like these separate things are always going to be these like X sums are always going to be sorted essentially as lists, then this is going to be like merge sort and it's going to be fine. If A1 is less than B1, yeah, it's just merge sort. Well, that's fun. Okay, another couple of random lemmas about rings here. I guess the point is that like we had these because because they're used here. The point is that these are all used. Again, it's like this Q, this quotation expression. Does it tell me the type? The type is like a Q. This is interesting. So like capital Q is the type, whereas lowercase q is the quotes the lean expression. Q of t quotes the lean expression t into a Q A if t is of type alpha. Okay, so this is how I like generate. When the lean info view asks me for something of type like big Q parenthesis, I have to like do little q of something. It's like a good like thing to remember. One mole. Yeah, a bunch of stuff here. Cool. Mole PF left. Mole PF right. Mole PP PF overlap. These are just like further theorems, right? They're theorems about rings. Yeah, okay. They're just like generic theorems about rings that we need. Because we're about to do eval mul prod, right? So just like we do eval add, now we do eval mul prod, which is very similar, right? X, Y for X, Y coefficients, we just like multiply them themselves. For X a coefficient, we take X out in front. For Y a coefficient, we take Y out in front. Wait, what? No, sorry. The point is that, like, the coefficient always goes at the rightmost side, and it's always this. Okay. X to the EA times A2 times X to the EB times E2 is X to the EA plus EB times A2B2. If they are identical except coefficient. Right. Wait. Yes, if they are identical except for their coefficient. And then we have A1, A2, B1, B2 equals this, and then it's again, it's like merge sort. Eval mul prod. All right, cool. Some more theorems. Okay, this is not a theorem about. This is eval mul 1. Multiplies monomial to a polynomial to get a normalized result polynomial. A times 0 equals 0. A times b1 plus b2 equals a times b1 plus a times b2. Sorry, did this do like the cancellation? Yeah, there's nothing about like the cancellation here. The cancellation uses eval add overlap. The point is that eval add overlap adds them together, right? So whenever I'm adding two monomials, that's when I have to like try to detect overlap. eval-mul 1 and eval-mul. Basically, it's like the left-hand side and the right-hand side. Apply nat.cast to a cast polynomial to produce a polynomial in alpha. Atom E causes E to be allocated to new atom. A sum delegates to X sum eval nat cast. X base eval nat cast. Applies to a polynomial to produce a polynomial in alpha. And at some point I need to like factor my polynomials. Or like, you know, like when I have a polynomial, when I have like x to the like power 3, I need to do first outside, inside, last to that. Eval nat cast, x prod nat cast. Okay, and we also have like the scalar multiplication. That's sort of cool. Just gonna like skip some of this. Pow 1, pow. Okay, is this. Wait. Attempts to prove that a polynomial expression in n is positive. 0 greater than 0 fails. 0 greater than a plus b if 0 greater than a, or 0 is less than b. Sorry. Is 0. The point is that we need to detect when it's 0. Attempts to prove the monomial is positive. Why do we need these? Atoms are not necessarily positive. The main case of exponentiation of ring expressions is when VA is a polynomial, n is a non-zero literal expression, like x plus y to the 5. In this case, we work out the polynomial completely into a sum of monomials, right? Right, okay, so it's actually doing, it's not actually doing like unary representation of naturals, it's doing binary representation of naturals. Or is it pow 1, pow bit 0, pow bit 1? Okay. X to the power 1 is x. Yeah, all of this makes sense. I'll pound that, yeah, so we can decompose. So we're fine with that. There are several special cases when exponentiating monomials. 1 to the n equals 1, x to the y equals x to the y, 1 x and y are constants, a times b to the e equals a to the e times b to the e. Extract coef. Make cache, eval cast, eval atom. Skipping more and more. Divides two polynomials via VB to get a normalized result polynomial. Right, so we have these like inverses. And that's one thing, is like I need to not have inverses. I guess that's like something we dealt with separately from the from like the main tactic. It would be cool if there was like a big ecosystem of more sort of like more of like the lower level tactics exposed, and the higher level tactics were written as combinations of the lower level tactics. Like, is there a tactic in MathLive that will just like take an expression with lots of divisions in it? I guess that's field simp technically, but I feel like field simp isn't like re-expressed a over b equals c as a equals b times c. Is atom or derivable? Not the same as whether the result of eval is an atom. Evaluates expression E of type alpha into normalized representation as a polynomial. Main driver of ring, which calls out to eval add eval mul. So this is the main driver of Ring. This is the one that like really it calls all of the things that we had before, and it just, you know, it just simplifies it, you know, it makes it right. And I guess the point is that Ring 1, what exactly is Ring 1? Is Ring 1 like the normalizer that puts it into the normal form? The Ring 1 does not normalize the sub-expressions in atoms. Right, okay, so the point is that I think I understand what this is saying. The Ring 1 normalization basically normalizes the whole thing. But if I have something like A mod B, right, if I have something like A mod quantity, like B plus C times D plus E, right, it's not going to normalize the B times, or the B plus C times D plus E because it's like within this sort of like mod expression. That's what that's saying. All right, that's fun. So basically we eval the whole thing. We like recursively call ourselves to like eval mo. We have to like eval all the sub-expressions. And then we like compose them all into one big thing. And then we prove things are equal. Sorry, let me like return to my own version of this file. I have like a copy that I've made. We prove these equalities. So I think the upshot is most of this file is gonna have to go out the window for what I want to do. I think the point is, what I would what I want is to get things into the form of multivariable polynomials. Get valuations of multivariable polynomials. Can I detect all of the atoms? Right, because this is basically, this whole like file is a like really clever way of doing merge sort in some ways. It's just like a way of like, yes, I will recursively define, you know, functional programming is great. I'm going to recursively define everything so that when I call eval on my big expression, it just returns a huge normalized polynomial expression that I can then compare to my other huge normalized polynomial expression. That's not what I want to do. I want to like keep things in the form, right? I don't want to be doing any, you know, exponentially. I want to be doing linear time computations, basically, always. And so what I would like to do is I would like to convert, I mean, like, maybe the point is that I should get rid of all of this, and I should just, like, do, right, one thing. Yeah, let me, like, write a little note to myself. The point is, like, this. Well, this file is basically not useful for me. Most of this file is about normalizing expers in exp time. I don't want to do this. What I want to do is like one, detect atoms. One, detect all the atoms. Two, make a type with as many elements as atoms. I wonder if I can just make it like question. Can I just make it like a multivariable polynomial over the type of like expressions? That would be pretty wild. Do like question. Can I just make a MV polynomial over the type of exprs itself? That would be pretty wild if that works, but I don't see any like barrier to it. Okay, so like make a type with as many elements as atoms, with an element for each atom, I should say, an element for each atom. And then what I want to do is like prove that E1 is equal to like okay, so what I want to do is like make a polynomial P1 of type MV polynomial, atoms R. And then what I want to do is I want to prove that E1 is equal to P1 dot eval on like fun, the function that takes like A to R, right? Like it takes like quote A to A or A to quote A. This is where I need to like get this right to like anti-quote A, right? To like because A is an atom. It's like an expression. Like I want like atom expressions. I just want to like this is the type, but this is a type of atom expressions, right? This is A of type of atom expressions, and I want to go to like the antiquote of A, which is of type R, right? Basically, I have P1, and then I'm like evaluating it on like, okay, all of these expressions have values. And then like same for E2, prove that E sub 2 equals this. Right. And then like, then the point is I want to claim that the polynomial itself is equal to 0. Or like claim P1 minus P2 identically 0. And then I have to then like apply randomized. Schwartz-Zippel. To prove this claim. The evals are equal if the things are equal. All right. It's all to do with this Q thing. Like these, all these symbols I think are like gonna be like Q something, and I don't know like how. Q, the type of lean expressions having type A. Maybe the point is that it's not like type of atom expressions, but type of like general expressions. Because the point is that like we do have some naturals in there that we want Ring.lean to interpret as themselves naturals and not just like variables, because then like we would be trying to prove like 2 plus 3 equals 5, and we would like choose a random value for 2, a random value for 3, and a random value for 5, and we would get that it's not equal. Which would not be workable. Right, type of atom expressions. The atoms, like a type with an elements for each atom, which is like, which is not a like rational number. Yeah, how does like Ring deal with like square root of 2? Will it like Ring will not prove, right, that square root of 2 times square root of 3 equals square root of 6. Right, type of atom expressions. A multivariable polynomial of the type of atom expressions. Q. Synth instance Q quotes the linear expression. Is there like an anti-quote? What if I go to the definition here? Macro rules. QQ macro. We do have like something about anti-quotes here. Anti-quote. Float level anti-quote. Float X per anti-quote. This one. Float X per anti-quote. Scoped syntax. Okay. Well, at least that's like a outline of a plan for doing this. I mean, detecting all the atoms is something that I can maybe figure out how it's done here. I could trace everything. Well, I'll save that. And I guess, okay, like what actually is going on? I'm here in Schwartz-Zippel, elliptic curve domain. I mean, what I should really do is like make that PR make this Schwartz-Zippel PR a draft PR rather than a in practice PR. Right, I mean, potentially they could, yeah, I don't know. I don't know if they like want me to do that or like they're cool with it. Just like posting a bunch of like random code to their repository. I don't know if that's necessary. Like, is it the right time to like start a project? It's not. The thing is, it's not in like mainstream MATLAB yet, so I don't like. I want to be developing. I want to be developing things, but I don't want to have to like make a new project that depends on MATLAB and then tell it to look for like this branch of MATLAB that I have. I don't know how to do that. Maybe it's not that hard, but okay. Anyway, I think that's enough for today.